Now I need to design 8 different adders, so I'm going to add it, a Verilog module. Let me rename this as adder underscore 1. Next, finish. I'm naming this as adder 1 module adder underscore a1 of sum comma a comma b, and I am to declare the ports output 8 down to 0, sum followed by input 7 down to 0, which is nothing but a, and input 7 down to 0, which is nothing but b. I'm just going to assign the value sum is equals to a plus b module, end module. Let me save it. Now I'm just going to copy this. I'm going to create a new file, Verilog module adder underscore 2. This is my second adder. So with respect to second adder, let me name it adder 2. So this is with respect to second adder. I must increase 1 by 1 bit, so this will remain to 9 and the value of a changes to 8. Rest will be as it is. I'm just saving this. Again let me copy it and I'm going to add. File name that I'm giving is adder underscore 3. So this is with respect to my third adder now. It is going to get incremented by 1 and this 2. Let me save it and copy it again. Since we need to include total 7 adders, right? Adder underscore 4. This is my fourth adder followed by a4. Now this gets incremented by 1 and this 2 will get incremented by 1. Let me save this, copy, new source, Verilog module adder underscore 5 now. Let me change this to 5 and this to 5, and it's get incremented by 1. This 2 will get incremented by 1. Save it. Similarly, this is my sixth adder, last but one adder. This get incremented by 1, 13. This get incremented by 1, 12. 7 down to 0. Let me save it. Adder underscore 6. I need to include the last adder. Seventh order. Next, finish. A7, and this range 14 down to 0, and this will reach to 13 down to 0. Now let me save it. So these are my adders. You can see here on the left side, first adder, second adder, third adder, fourth adder, fifth adder, sixth adder, as well as seventh adder. This I need to change. Save it. Fifth adder. So it's get incremented by 1. Now what is the part left? I need to design D flip-flop, right? So I am going to add new source, module D flip-flop underscore 1. Let me take only one D flip-flop. I will be repeating it again, right? Let me name it as D flip-flop with clock. Module D flip-flop 1 underscores, let me give some name 4-bit, for which Q will be acting as output, D will be acting as input, there will be a clock, and let me put clear also. Output will range 4-bit, 3 down to 0 Q, so as well input 2. I need to declare register 3 down to 0 for the output. Within the sensitivity list, I am talking with respect to passage of the clock. I am assigning to 0. Else begin Q is equals to D followed by end module. So this is my D flip-flop program. Let me save it. Now the last thing, I need to take a top module and I need to instantiate all the lookup tables and all the multipliers for a 8-tap filter. So let me add new source. This is my top module. Which is of 8-tap. Let me start with module. So I'll need to assign what is my highest range, 15-bit, right? Which is a Y, comma, I need to assign X, I need to assign clock, I need to assign clear. Next thing is, I'm going to assign the ranges, which is a 15-bit, so 14 down to 0, followed by Y. Input I need to assign with respect to 4-bit, so 3 down to 0, followed by X. Input I need to assign clock and clear. Now I need to assign all the Ys which are required. One Y required is 4-bit, 3 down to 0, XM1, XM2, XM3, XM4, XM5, XM6, XM7. Next, let me go for a wire which is of 8-bit, 7 down to 0, W1, the first wire that I have assigned. Second will be incremented by 1, so W2, the third one 9 down to 0, this will be W3, the fourth one 10 down to 0, this will be W4, similarly 11 down to 0, this will be W5, wire one more 12 down to 0, this will be W6, finally 13 down to 0, this will be W7. So these type 7 wires are required, and the last wire that is needed at the end is 8-bit representation for the V signals, right? V1, V2, V3, V4, V5. We have seen till V6, right? V7, right? V6 and V7. Now I need to instantiate. If you see multiplier, where is my multiplier? This is my multiplier, right? What is the name I had given here? Multiplier underscore 4. So this I'm going to copy it. I'm going to present here with an instance name m1 of w1 comma x. I'm just trying to assign my wire signals. Similarly, what is the name I'm given for D flip-flop? Copy, paste it. Let me give some name D1, xm1 comma x comma clock comma clear. Similarly, multiplier underscore 4, I'm copying this for the second multiplier. So M2 followed by V1 and XM1. The next will be, I need to take first adder, and where is my first adder here? And the model name of my first adder is something is copy, Control V, let me type this instance name as A1, W2 comma W1 comma V1. For the second flip-flop, I need to take D2, this will be XM2, XM1, clock and clear. Now I need to take with respect to third multiplier, I name this as M3, V2 for this M3, this instance will be V2 and XM2. Similarly, now let me take second adder, add instance name at A2, this 2 will be A2, W3, W2, V2, this will be W3, this will be W2, and this will be V2. Again let me take this D flip-flop, instance it here, name this as D3, here it ranges to third one, X3 followed by X2, XM3 followed by XM2, and clock clear. Now let me take my fourth and the last multiplier with respect to 4. I am assuming this will be M4, this will be V3, and this will be XM3. Now let me take one more D flip-flop here. I am assuming this to be D4, which will be XM4 followed by XM3, clock as well as clear. It doesn't matter whether I am writing it in order or not, because Verilog will take all the commands in concurrent, right? So you really don't need to worry about the order. Let me consider this to be A3. This is A3 followed by W4, W3 and V3. Now let me take multiplier 8 coefficient. Since the command is value of 8, here we can check this whether, let me open this, see here it is multiplier underscore 8. Let me copy it. This is as it is. Now this value will remain to M5, V4 and M4. Now again a D flip-flop is needed. Let me name this as D5, which will be XM5 followed by XM4, clock and clear. I need to add one more adder here. I'm just trying to instantiate everything, okay? I name this as A4 and this 2 as A4. This leads to W5, this leads to W4 and this leads to V4. Similarly, now let me take one more combo of multiplier. This entire combo of multiplier I am taking. I am just pasting here. This will be my M6 and this will be V5 and this will be XM5. Let me name this as D6, this as XM6 followed by XM5 and clock as well. Now this will be A5, this will be A5, this will be W6, W5 followed by V5. That is alright. So let me take one more combo, the last but one combo it may be. So let me consider total 8 multipliers, right? And now we are going for the 7th multiplier. This will be V6 and this will be XM6. Similarly, the value I am changing it to D7 and this to 7, this to 6 and this adder I am changing it to 6. This will be A6 followed by W7, W6 and V6. Now coming to the last multiplier where I don't need this D flip-flop, so let me remove it. This multiplier I am going to be M8. This is my V7 and this will be XM7 followed by, since it is a last adder which is the 7th one, and this will be 7. Output it is connected to Y, so I am assuming this to be Y, and this is to be W7 followed by V7. Now let me complete this module by writing end module. Let me save this. You can cross check here once how these are interconnected. By dragging this, we can cross check clearly. So ultimately this is my top FIR filter, top module, Within this module I got all the multipliers, and within this multiplier I got the encoder, control unit, NOR cell, as well as lookup table, barrel shifter, and within this barrel shifter I got the mux. Similarly, for all the 8 different multipliers we have designed this circuit. Now let's run it. Generate, post, place and route static timing completed successfully. Now let's check the waveform representation. Check for it is in simulation. Go to the iSimulator, double click on behavior check syntax, then double click on simulate behavior model. This will create a new window. So within these signals, this is Y is my output, X is my input, this is my clock and clear. Let me give the clock value. Leading edge as 1, trailing edge as 0, a period of 20 with a common 50% duty cycle. Initially let me give clear value to 0. Since it is active low, I am giving value to be 0, and the input X I am giving a value 0010, which is nothing but 2. Now let's check its response. So what is the value I got? Even after running many times, you can observe that there is no change in value, right? Now let me change the clear value to 1 and observe its response. Probably in Xilinx you are getting a response like this. Let me change the value to radix, unsigned decimal. See here, we are getting the result. This is my radix unsigned decimal. Initially the input that I am giving is 2, and the last clock cycle the value that I will be getting is 96. In order to see the intermediate in between within the FIR filter, let me check it with the help of model sim. See here, so these are the same program that has been coded in Xilinx. Input for this model is filter underscore ATAP. Now let me first compile it. Compile all the files which are present that I am compiling here. Done. See here, it is compiling. Now I need to simulate. Start simulation. Under work directory, I need to search for my module name, which is a filter underscore ATAP. Click on OK. This will create a window for this. Now Y is our output, X is our input, and clock as well as clear I am going to get selected. Rest of all the intermediate nets or wires, that doesn't matter really. Now see, initially the input that I am forcing is 0010, for which let me consider active low clock, so I am assuming this to be 0, and a clock signal I am assigning. Now run the program. You can observe that even after running many times there is no change occurring. And what is this value? Unsigned. Only for the first multiply it is having. Now when you are giving the clock clear signal to high value, you can observe that it will act as a FIR filter. See here, for the first clock cycle it will be remaining as it is for 8, for the second clock cycle 16, third clock cycle 24, fourth clock cycle 32, 48, 64, 80, 96, and it will remain as it is. I hope this is clear to all. In order to see the top model, now let's me go for the implementation mode. Within this implementation mode, I need to go for design utilities. Let me first check this. Now I need to go for the design utilities, create schematic symbol, double click on it, yes. Later, now goes to the synthesis. In order to view the RTL schematic value, double click on view RTL schematic. It creates a new dialog box. Click on OK. So this is my designed FIR filter, 8-tap FIR filter, where you can see all the intermediate connections that we have designed using Verilog. And in order to see the synthesis report, you can go to here, design summary, and within design summary, just scroll down, you will get the synthesis report in a more detailed fashion here. And this is my synthesis report generated. At the end, you can able to see what is the total number of delays which has been occurred in terms of say nanoseconds. So finally, you can observe that it requires total of 8.95 nanoseconds for designing this FIR filter, 8-tap FIR filter.